Hi everyone, and we're back again. This time we're going to extend our idea of reactivity and start looking at the electrochemical series. So let's get started. So essentially we're going to define the electrochemical series and look at it in terms of being a reactivity series that we can use to predict redox reactions. Okay. We're going to look at the definition of the hydrogen electrode, including its components and conditions that you need to know. Restate and define the conditions associated with standard laboratory conditions, or SLT, or standard temperature and pressure. Okay, and then be able to use the electrochemical series to predict redox reactions. So this is just going a little bit further beyond what we were looking at in terms of predicting the oxidant and the reductant for single displacement reactions, and actually using our electrochemical series to predict redox reactions and draw half equations from them. So let's get started. Okay, so the electrochemical series, which is in your data booklet and should always be used when we're talking about redox reactions, okay, was created by experiment. It's an empirical measurement. It's been created by experiment like so many of the other constants that we have in chemistry. And it shows the relative reactivities of metals and their corresponding cations. Okay, so we're looking at things like copper solid compared to copper 2+. Okay, and essentially what they needed to do was to be able to rank all of these metals and their cations. They needed to create a standard half cell in order to define a 0 point. Okay, and we're going to learn more about half cells as we move on. But at this stage, it's just essentially one part of what we will come to know as a cell or a battery. So all other cells, which is essentially an electrolyte and electrode, could be connected to this half cell and then figure out if it generated a positive voltage or a negative voltage. And essentially from that, we could work out whether or not they were more reactive or less reactive than that half cell. So that is known as the standard half cell or the standard hydrogen electrode. And this is something that we need to be able to know the components of and the electrolyte solutions as well. Okay, so this is a picture of our standard hydrogen electrode. We have a voltmeter, which has an external wire, which forms our external circuit. Okay, this is our external circuit. This one here is the hydrogen electrode. And then what we end up with being attached to the hydrogen electrode is the metal that we're testing in a electrolyte solution, so a solution that can carry a charge. Okay, so we have an external wire which gives us the external circuit, and then this thing in the middle basically closes the internal circuit, completing the circuit and allowing charge to flow. So essentially what we have here is then gas is bubbled in. Okay, so we bubble the gas in through a tube, and it is put around what is essentially a inert electrode. So something, this could be graphite, but hydrogen is usually platinum. Okay, so a platinum electrode. And this puts all the gas ready to react around this porous platinum electrode. Okay, and in here, the solution is usually an electrolyte and acid solution. So we've got H plus in it as well. So we've got H2 and H plus. So we state that the most reactive metals are those that are oxidized more readily. Okay, so they're the best reductants. So if that's the case, then they are oxidized more readily than the hydrogen. And the most reactive metal cations are those that are reduced more readily. Okay, so the best oxidized ones. Okay, so this is exactly the same as what we looked at with the normal reactivity series. We do need to know what the hydrogen electrode is made of, so we usually have 1 molar solutions in here, and this would be an acid solution, H plus in this case. Could be HCl or another dilute acid, but at 1 molar. So the other thing that we need to know about with our hydrogen electrode is it is created under standard laboratory conditions. So for all measurements on the electrochemical series, the relative reactivities are measured under standard laboratory conditions. If we deviate from these conditions, then they may not react in the same way. Okay, so if we observe non-standard results, then it could be because we need to check whether or not the system was at standard conditions. So standard conditions is 1 mole per decimeter cubed for all solutions, the electrolytes and everything else, and then 1 atmosphere pressure for gases. Okay, so this is 100 kilopascals, and then our 25 degrees C, otherwise known as 298 Kelvin. So 298 Kelvin for our temperature, 100 kilopascals for our pressure, and 1 mole decimeter cubed for our solutions. If we have that, then all the conditions are said to be standard. So we have standard laboratory conditions, and the electrochemical series should hold. So this is the electrochemical series in your data book. It's table 14 in your data book. What it actually does is it runs strongest oxidant on the bottom left-hand corner here, strongest reductant on the top right-hand corner there. I highly recommend that you annotate your copy of the data booklet with this, because it will help you start to learn the way we're going to use it for predicting. When we read the half equations, and you'll notice that they're half equations, everyone on the left has electrons. So as we move from left to right, we're looking at the reduction equation. So left to right for all of these would be a reduction equation. Okay, this double-headed arrow indicates that it could be read from the front or the back. Okay, so if I wanted to read the reduction half equation, I would read from left to right. However, if I read from right to left, I would get the oxidation equation. Okay, so we can use this to predict whether or not a reaction would be spontaneous. If you think back to the original activity series, we said if it was higher, it was more reactive and it would displace. In this case, the strongest oxidant always reacts with the strongest reductant, which means that if we have a positive gradient going from left to right, then we can observe a reaction happening. And if we go back to our old example of copper solid, which is here, and placing that into a solution of silver nitrate, which is essentially silver ions because the nitrate is a spectator ion, you can see I can draw a positive gradient from left to right. I know that the forward reaction will occur for the one going from the left to the right. So Ag plus an electron gives me Ag solid. And I can draw the reaction going from copper from right to left, which gives me copper solid going to copper 2 plus. So you can see from this we can pull out our 2 half equations. So copper solid goes to copper 2 plus aqueous plus 2 electrons, and this is my oxidation equation going from 0 to plus 2 on my oxidation states. And then I have Ag plus an electron goes to Ag solid. Okay, and again, now we can look at these, write the overall equation. We would have copper solid. I need to multiply my silver by 2 to get my 2 electrons. 2 Ag plus aqueous. Now my electrons will cancel. Will give me Cu2 plus aqueous and 2 silver solid. Okay, so we can use the electrochemical series as a really good way of pulling out our half equations and seeing which way they're going to go and using them to predict. So if we have a look at another couple of examples, we can say we have a zinc electrode and a copper electrode. So in this case, we would have copper 2 plus reacting with zinc solid. Okay, and this reaction would occur, it would be spontaneous because I'm going to get this positive gradient from left to right. So let's look at another example, this time with zinc and lead. And we can see that again, lead is still below. The lead 2 plus is the stronger oxidant, so it will be reduced. Zinc is the stronger reductant, so it will be oxidized. Again, we have this positive gradient and the reaction would be spontaneous. Last one, if we have a look at this, now we've got a different situation. In this case, our zinc solid isn't going to be oxidized. It is now lower, so I don't have a positive gradient. Here, it would actually be a positive gradient from Zn2 plus up to our magnesium solid. Okay, so in this case, the zinc will actually be reduced because it's being reacted with a more reactive metal, magnesium, and the magnesium will be oxidized. Okay, so we could then write out the overall half equations and then draw the full redox reaction. So essentially, we use the electrochemical series to be able to predict redox reactions. The strongest oxidant will always react with the strongest reductant. So we circle the species that we have, find our positive gradient. The reverse reaction for the reductant is our oxidation. The forward reaction for our oxidant is the reduction reaction. And then we can draw our two half equations, multiply to cancel out the electrons, and draw our overall redox process. So this is just a couple more examples here. You can see that chlorine gas would spontaneously react with copper, lead, or iron. Copper 2 plus would only react with lead or iron, and lead would only react with iron, okay, because all the others don't form that positive gradient. So going straight across or going down won't give us a spontaneous reaction. And what we're looking for is that spontaneous reaction. Will the reaction go without us having to force the reaction along? So this is your chance to practice this, okay? So for each of the following combinations, I want you to, in your notebook, have a go and determine whether or not a reaction will occur. And if it does occur, write out the half equations for it, okay? Once you've done the half equations, write an overall ionic equation, and then bring those to class and we'll go through them. Hopefully you had a go at those. If you're struggling, just remember to bring them and ask questions so we can clarify. But essentially from this, you should be able to define the hydrogen electrode, make sure you have good notes on that, understand the electrochemical series was created by comparing reactivities to the hydrogen electrode, know the conditions for SLC, and be able to use the electrochemical series to predict spontaneous reactions. I'll get another quiz up for you guys to check how you're going, and I'll see you in class.